Hello. So I was looking at some kinematics equations today, just kind of reviewing, and I have some thoughts on this because I believe that, unfortunately, the way that physics is taught is that you start physics uh, pretty early. I think it's as soon as you finished Calc 1. And the idea, I mean, I understand the reasoning. It's because if someone's really wanting to study physics, they're not going to want to wait till they get through 4 semesters of calculus before they start physics. But really, I don't I don't think you should do that. I believe that you should have 4 semesters of calculus before you even start physics. And so the reason is the 4 semesters of calculus would be Calc 1, 2, 3, and 4, or to give more descriptive names, um, derivative calculus, integral calculus, multivariable calculus, and vector calculus, and then differential equations. Those are kind of like the broad topics that are covered in each of those classes, with a few other things sprinkled in there. Um, and to be honest, vector calculus, which is usually covered in Calc 3, um, as well as differential equations, can be used and really probably should be used from the very first moment that you start studying physics. You can do physics without those concepts, but ideally you should already be using those advanced mathematics concepts when you're applying them to your first physics problems. Otherwise, I think but you'll just have to redo the problems after you go through them the first time, and I don't know, to me that just seems counterproductive. So anyway, I wanted to go back through this and solve it a different way that I think will be pedagogical. Um, so and also to say to that, because so you can typically this problem would be solved um, by a student by just having memorized a handful of kinematics equations and then applying basic algebra to those kinematics equations to solve for uh, what is needed in this case. And that's fine, and there's nothing wrong with that, and a lot of things can be solved that way. But I just, to me, that's one of the differences between, say, like someone who is using these, say, using physics or using mathematics as a technician level versus someone who's more like, say, a physicist, a scientist, or engineering level. I believe that it doesn't take much work to train someone to be able to just have the formulas and apply the formulas. Um, but it takes a great deal more work to be able to derive the formulas. And to me, being able to derive the formulas is one of the main differences between uh, physicist, scientist, engineer versus like technician level. And so that's why I don't think that physics should even be taken until you have all of this calculus under your belt, because then you're using calculus to derive the formulas as you go instead of just plugging and chugging formulas that you've memorized. Because plugging and chugging, like I said, pretty much anybody who's had high school mathematics can do that without any real effort. Maybe just a semester of here's how you use this formula or something like that. Anyway, so there's my rant. So that's why I'm going to solve this a little bit of a different way that I hope will be uh, useful for those purposes. Um, all right, so here's the problem. We have this character Sam, and Sam is driving her car at a constant 40 meters per second when she passes Charlie, who is sitting at rest on his motorcycle. Charlie instantly begins accelerating at 9 meters per second squared. So then the question is, how far does Charlie have to drive at this constant acceleration to overtake Sam? So I've already written down, to save a little bit of time here, the things that we can draw from this. So we see that the velocity initial of Sam equals the velocity final of Sam. Her velocity does not change, and it is 40 meters per second. We see that the velocity initial of Charlie is 0 meters per second. He's sitting at rest. The acceleration of Sam is 0 meters per second squared. She is at constant velocity. She's not accelerating. And the acceleration of Charlie equals 9 meters per second squared. which is given right here. And then our question is, how far does Charlie drive to overtake Sam? Now, just want to delete a bunch of this stuff to get what I have behind it. Okay, so now what we have here is kind of a pictorial representation of what's going on. We see that this would be the initial state of things, and this would be the final state of things. So initially, Sam is cruising along at 40 meters per second, and Charlie is at rest. Then at some point as they're driving, they will be driving, they'll have met up with each other so that they're like side by side, because when they'll be side by side here when Sam passes Charlie, but then Sam will initially overtake Charlie because Charlie's not moving. But then once Charlie starts to accelerate, since Sam has constant velocity, as long as Charlie accelerates for a long enough duration, which we're just assuming that he does in this case, then eventually he will end up passing Sam because his momentary velocity will be higher than Sam's, and he will have driven far enough at a higher velocity to have passed Sam. So that would be this final condition where they're once again side by side, but now Charlie is moving faster. And just to draw this out using, I guess, say like vectors, and you have to use a little imagination here because ideally the length matters quite a bit, but I'm not doing this with a computer, so it won't be exact. But let's say this is Sam. Sam's cruising along. These are velocity vectors. The magnitude of this vector represents the magnitude of her velocity, which is her speed. And so she's cruising along. All these vectors are ideally the same size. They should be the same size. I'll do one more in there. Okay, so this represents the movement of Sam, and if say each one of these is the same time interval, so maybe a second or something like that, then we have a different sketch for the movement of Charlie. So let's say this is the point where initially Charlie's velocity is 0, but then he starts to accelerate right afterwards. So I'll kind of draw another dot like almost right on top of it. So those will be like the first 2 seconds. He's moving really slow. Then the next second, he's moving faster. The next second, he's moving even faster. The next second, he's moving even faster. The next second, he's moving even faster. And so you get the idea. And so these would be like seconds 1, let's use green up here. First second, second, third, fourth, fifth, sixth. And then for Charlie, we have the first and the second are practically right on top of each other. The third is a little farther away. Fourth, fifth, sixth. Oh, that was kind of lucky. They happened to line up. So I don't actually know yet whether it'll be 6 seconds because I made up these lengths. But this is the idea. So at some point, we see that the velocity of Charlie here, this is much longer than this line, but they meet together at the same point. So in the next second, Charlie will travel even faster, so he'll travel even farther. There's a correlation between the length of the velocity and the distance. And we'll see that poor Sam has still just traveled the same distance. So at the 7th second here, they would have passed, Charlie would have passed Sam by quite a bit. But what we would be concerned with here is the 6th second, the moment that the overtaking happens. So just to really beat down what conceptually is going on in the problem, that's what's happening. Now, let's use blue. So let's go ahead and set this up. And where I want to start is I do want to start with a formula that happens to be memorized as one of the kinematic equations, but I just feel like this formula is so basic that it doesn't even need memorized. So that's velocity final equals velocity initial plus acceleration times time. And I feel like this is really obvious because so velocity final is is kind of obviously equal to the acceleration over a certain time period. I feel like if you just think about the concepts, it's kind of a given that that's what that means. The acceleration over a certain time period is going to get us to our new velocity, but it also matters what velocity we start at. So it's the velocity that we start at plus the acceleration times the time is equal to the velocity final. If you wanted one more explanation of that, you could say that it's also kind of obvious that the change in velocity equals, oops, I didn't write the velocity symbol. Change in velocity is equal to acceleration times time. Otherwise, you could say the average velocity equals the acceleration times time, but here I want to think of it as the change in velocity is equal to the acceleration times time. Change in velocity equals velocity final minus velocity initial, which is equal to acceleration times time, and we see that velocity final equals velocity initial plus acceleration times time. So in this sense, we haven't really necessarily memorized this. It sort of just comes straight from our understanding of the concepts. And what we're going to do with this then, this is what I want to make sure I do it the same way I did before. What we're going to say, so what we are concerned with is position. We want to know how far does Charlie drive? That is a position. And I should be using S's. I'll probably end up using X's because I'll probably accidentally write an X anyway, even if I try to use S's. And also, since I have Sam as an S, maybe it'll be a little better to use X's for the position. So yeah, so I'll use X's. So what we want to know is we want to get some solution for X. So basically, we want to find X of t, really, is our goal. And the way that we're going to go about this is, so we understand velocity already. We're going to say that we have to understand that the change in position with respect to time is equal to velocity. And so now what we want to do is we want to say that the so we want to say that the velocity final of Sam is equal to the velocity final of Charlie. No, that's actually not true. Hold on a second. It's not the velocity that's equal. Why did that work, actually? We want to say that the position final of Sam is equal to the position final of Charlie. And there's the connection that I wanted. So we have, this is our end goal right here. The final position of Sam is equal to the final position of Charlie. And these are some relationships that we currently have, and just for whatever reason, I'm going to want to use this one right here. So we want to get from position to velocity. That's where I was going with this. So we know that the basic idea for applying calculus to motion, anyway, is, let's see, how do I want to set this up? So let's say that we have this these graphs here. Okay, and in each one of these, the x-axis will be time. I should say the horizontal axis. The horizontal axis will be time. The vertical axis, let's say that this is position as a function of time. let's say that this one would be velocity as a function of time, and let's say that this one would be acceleration as a function of time. To get from position to velocity, from this graph to this graph, we take the derivative of position with respect to time. To get from velocity to acceleration, we take derivative of velocity with respect to time. To go this way, we're going to take the integral of acceleration as a function of time, dt. And to get from velocity to position, we're going to take the integral of velocity, there we go, dt. So now, this is our end goal. The final position of Sam, when is the final position of Sam equal to the final position of Charlie? Well, we see from this over here that position, if we have velocity and we want to go to position, so right now we have a formula that we got from first principles for velocity, and we want to get to position. To go from velocity to position, you take the integral. So we're going to say you take the integral of velocity. So the final position of Sam is equal to the integral of the final velocity of Sam with respect to time, which is equal to the integral of the final velocity of Charlie with respect to time. Now, see if I missed something, or what do we want to do next here? Yeah, first we'll just plug in. So we'll go ahead and plug these in now. So the integral, and I'm going to end up applying bounds. I just don't feel like doing it yet, so I'll do it later. We see that the final velocity of Sam is going to be equal to the initial velocity of Sam plus the acceleration of Sam times time. The time, for our purposes right here, is the same between Sam and Charlie, so it's just time. There's no time Sam, it's just time. dt. This is equal to the integral of velocity initial Charlie plus acceleration of Charlie times time dt. I could continue working this out mathematically, but at this point I want to go ahead and plug some values in. Not all the values, but I just want to plug in the values where things go to 0, because it'll make the rest of the math easier. I can pretty much ignore the stuff that goes to 0. So looking at our handy little toolbox right here, I've heard somebody call it that before. When we're dealing with Sam, the acceleration for Sam is equal to 0. So this term goes to 0. When we're dealing with Charlie, the initial velocity goes to 0. So this term goes to 0. So we're just going to have the integral. And now I'm going to go ahead and plug in the bounds. So we're going to go from time initial to time final. Well, time initial, we'll just call that 0, because that's pretty standard to say that the starting time is 0 on the clock. And then the final time, I'll try to be consistent here and call it time final. I would just write t, but technically I'm also going to write t inside the equation, so there's a difference between the t in the bounds and the t in the equation. So just to show that, I'll give this a different label, so I'll call it time final. And then this is velocity initial Sam dt equals the integral from, we're dealing with time again, so we're going to go from 0 to time final of the acceleration of Charlie times time dt. And something I want to emphasize here, because I think, I don't know, for me it was, I don't know, because of maybe high school math, that when I first started doing these kind of problems, I was thinking of it as a formula. And it's not a formula, it's basic principles, and then mathematics, which is just logic and relationships. So you're just applying like the rules of logic governed by the given relationships between the values. You're just manipulating those algebraically or by other mathematical means until you get to what you want. And so at any point here, these are true statements. So if at some point the final position of Sam is equal to the final position of velocity, then it also must be true by the rules of logic. Since this relationship is true, this relationship also must be true. This integral is equal to this integral. Well, and if that's true, then this must be true. And if these really are the conditions, that some of the conditions that we're starting with, then me canceling these out also must be true, which means that this must be true. And so that's kind of like the flow of what's going on here. Yeah, so we'll integrate this. We get velocity initial Sam times time final, well, yeah, times time from the bounds 0 to time final. So this is going to be this times time final minus 0, which will be this times time final. Time final, which is equal to, on this side, we're going to end up with 1/2 acceleration of Charlie time squared evaluated from 0 to time final, which would mean that we take time squared, we plug in the time final, we get time final squared, and then we subtract this 0 squared. So I can actually just change this to time final. Okay, so yeah, so let's see, what do we want to do next? Our goal is we want to get this position. Where did I go with it before? So we can solve for, okay, well, I think we want to solve for our times. So let's set this equal to 0. So we're going to get 1/2 acceleration of Charlie times time. I'm not going to write the final. Since our starting time is 0, the final time is time. It's our total time. It's our change in time. It's our time. Squared minus the velocity initial of Sam times time equals 0. Now we're going to solve this for 2 time values, and these 2 time values will be the 2 points at which Sam and Charlie are side by side. One of them being our first starting time value, initial time value that we don't care about, and the other one being our final time value, that's the time that we actually do care about. So let's solve this for time. We factor out t, we have t times 1/2 times acceleration of Charlie times time minus velocity initial Sam equals 0. And so our 2 time values are, one of them is t equals, well, one of them is t equals 0, and the other one, then we're going to say 1/2 acceleration of Charlie times time equals the velocity, no, not equals, it's minus, sorry, minus the velocity initial of Sam equals 0. So we have, for solving for time, we're going to add time to the other side, velocity initial of Sam. We're going to multiply by 2, and then we're going to divide by the acceleration of Charlie equals time. And then the other value, yeah, just, it's not going to look proper for it. The other value was 0, which we're not concerned about because that's, this first value is times 0. So this we're going to want to use. And I'm going to go ahead and write this down here because I'm going to need this. T equals 2 times the velocity initial of Sam divided by the acceleration of Charlie. And now we shouldn't need any of this, I don't think. No. So what we're going to do now that we have a time value, we have, I didn't write them out both out fully, but we have two equations using this, one for Sam and one for Charlie, and both of them can be used to give us what we want. So let's see if I do this right. Yeah. So what we're going to do is, let's say that we pick one. We'll say the velocity final of Sam equals the velocity initial of Sam plus the acceleration of Sam times time. So we have this formula, and now what we want to do is we want to use this formula to find position. So we know that the derivative of the velocity final of Sam with respect to time equals derivative with respect to time of the velocity initial of Sam plus acceleration of Sam times time. And then just make sure I'm tracking with what I did earlier. No, that's not right. Velocity is equal to the rate of change of position. So the rate of change of position with respect to time is equal to, and I did not actually want to do dt there yet. Alright. Gonna be a few mistakes in the video. Alright, so let me backtrack a second. So we know that velocity final of Sam is equal to the rate of change of position. I think we still want final. We definitely want of Sam. I think we want a final. I'm going to write it, but I would have to pause and think for a second whether that's we actually want final there or not. So we'll just leave it for now. With respect to time is equal to, there we go, this is looking better. Velocity initial for Sam plus acceleration of Sam times time. Now we can multiply both sides by dt. We're going to have dx. I'm going to leave this final Sam thing there because I think it should be there. Velocity initial of Sam plus acceleration of Sam times time, all times dt. Now we can integrate both sides. And what we're going to want now is we'll put bounds in again. So this is now dx, not dt. So we're going to use x initial, x final, which in this case I can also say that x initial is equal to 0 because what I actually want is the length from the initial point where they're all lined up together to the final point where they're lined up together. So we're going to call this 0. And once again with time, the initial time, we'll call that 0 to the final time. I'll label it TF here, and then I'll get rid of it eventually later probably. So I don't actually know that we wanted final right there. But anyway, so this is the position so this would be x from 0 to xf, which is going to be xf, and we'll throw the Sam in there because it's still dealing with Sam, is equal to, this is going to be VIS times t plus 1/2 acceleration of Sam times time squared, evaluated from 0 to TF, but once again, TF can, when I plug that in, I'm just going to have TF minus 0 here, and then TF squared minus 0 squared here. So it's really just going to be TF here and TF here, which I can just call T. So I'm going to do that. I hope that was clear. So this now is my new equation, and here I should be able to use it because velocity initial Sam is equal to 40. We have 40. Oh, well, sort of. Actually, I don't want to plug in numbers just yet. So because I need this time value is what I calculated earlier. So this is going to be x final of Sam is equal to velocity initial of Sam times 2 times velocity initial of Sam over the acceleration of Charlie plus 1/2 the acceleration of Sam times 2 times velocity initial Sam over acceleration of Charlie squared. And let me check to see if something goes to 0 here. We have velocity initial Sam, that's not 0. Acceleration of Charlie, that's not 0. Right here we have acceleration of Sam. Acceleration of Sam is 0, so this whole term is going to go to 0. So we're going to be left with the final position of Sam is equal to 2 times the velocity initial of Sam squared over the acceleration of Charlie. And now I want to do the same thing. This would be my answer once I plug in the values, but I want to just do the same thing with the using Charlie's equation for velocity instead of Sam's. So we would have right here, velocity final Charlie is equal to velocity initial Charlie plus acceleration of Charlie times time. And this time, the same deal, the rate of change of the position of Charlie with respect to time is equal to, I don't think we actually want the final right there, so I'm going to leave it off this time. I included it over here, I left it off here. I'd have to give a little more thought as to which is more correct notation, but velocity initial Charlie plus acceleration of Charlie times time, multiply both sides by dt. We have dx Charlie equals vi Charlie plus acceleration of Charlie times time dt. And this time I'm going to go ahead and plug in something that should probably go to 0 from this. This is Charlie. The initial velocity goes to 0. So I'm going to start ignoring this term now because I know that it goes to 0 eventually, so it's not going to matter. And I'm also going to integrate both sides. Once again, this is the position. It'll go from the initial position, which we'll call 0 meters, to the final position, which we'll call x final. This one is the initial time, which we'll call 0. And it makes sense to call it 0 here, to the final time, which I will just call t. I've been calling it tf, and then just changing it to t randomly later. I'll just call it t now. So what do we get on this side? We get x from 0 to x final. So we're going to get x final is equal to 1/2 the acceleration of Charlie times time squared from 0 to t. When I plug that in, this will just be t. Now we can plug in our time from this that we solved for earlier. So we get x final equals 1/2 times the acceleration of Charlie times 2 velocity initial Sam over acceleration of Charlie squared. X final equals 1/2 acceleration of Charlie times 4 times the velocity initial of Sam squared over the acceleration of Charlie squared. The numbers cancel to leave a 2 on the top, so x final equals, we have 2 on the top. The acceleration of Charlie will cancel with the 1 on the bottom, so there's just 1 on the bottom. Acceleration of Charlie. And nothing cancels with the velocity initial of Sam. So you notice these are the same. That's the reason I solved it the second time, just to show that the final position, this should have a Charlie there. The final position of Charlie is equal to the final position of Sam, which should happen because of the way that we set things up. That was the initial goal. Remember, initially we started with final position of Sam equals final position of Charlie, and we used this to get to all of this. Now, when we plug in our values, we have 2 times, what's the final initial velocity of Sam is 40, and this is in meters per second squared. The acceleration I have is 9. This will be meters per second squared. When we doing a quick unit check on the top, we're going to have meters squared over second squared. On the bottom, we'll have meters over second squared, but it's on the bottom, so we'll actually flip it. So you have second squared over meters. This meters cancels with one of these. The second squared both cancels, so we're left with meters, which is what we want. Our position should be in meters. Let's see if I can, how much I can simplify this in my head. I should have chose a little better numbers. It's not actually going to simplify all the way, but x final of Charlie is going to be equal to, I have 2 times 4 squared, which would be 4 times 4 times 10 times 10 over 3 times 3. So actually nothing simplified there. So I'll just plug this in the calculator the way it is right there and see what we get. So we have 2 times 40 squared divided by 9, which is 355, we'll say 0.56 meters. This will be how far they have traveled from the first point when they lined up with one another to the second point when they lined up with one another. And that's the moment when Charlie on his motorcycle overtakes Sam in her car. So this is the answer. And hopefully it was easy enough to follow. We didn't really have to memorize any formulas. We gleaned this formula from first principles pretty readily. And then other than that, we just took the relationships that we were given. Our goal right here, this was the relationship that we were seeking. And we took this and this formula that was gleaned from first principles and given information, and we combined them, did a bunch of calculus, and eventually we reached this value for our time, and then we plugged our value for our time into what we received for our position. So that's it.